So this video will summarize the discretization process that will end in a matrix form. And the idea is so that we can begin to discuss solution schemes in terms of, I'm going to change this to red, so that we can talk about the solution schemes in terms of these matrices, because it's easier that way. So in order to get here, I'm going to summarize the detailed procedures worked out in the previous 3 videos. So the equation we're trying to solve are the multi-phase equations. I can actually go back up one more, which we saw previously was in this form in a discretized version of the equation. This is a continuous form, is equations 3 and 4. And they are rearranged because right now they are as functions of pressure in the oil phase, pressure in the water phase, water saturation, and S0. So they're functions of SO, SW, P0, PW. And it's just 2 equations and 4 unknowns. So we introduced capillary pressure and the fact that saturation sum up to 1, and then ended up with these 2 forms of the equation so that they are in terms of PO and SW only. And again, we have introduced capillary pressure and the fact that SO plus SW equals 1 to get to this form. And then these equations have to be discretized. For the left-hand side, we use central finite difference 2 times. All right, and for the right-hand side, we use the backward finite difference. And I explained all of that in the previous 3 videos. And that's what is going on here, which ends up on the right-hand side with this kind of term. And you will begin to see this D11, D12, D21, D22. And it's all to get us to the matrix form, which facilitates communication regarding the solution schemes. So we do the same thing for water. On the right hand side, we get this discrete form in terms of D11 and D12. We discretize the left hand side, which I already explained at the beginning of module 4. Multiply both sides by volume as explained in module 4, and that gets us to the final form of the discretized oil equation shown here, which I call equation A. The oils are in green, the water is in blue. So now we do the same thing for the left-hand side of the water equation. Similar process, central difference 2 times, and then multiply through by volume, and we get equation B for water. And equation B, you can look at it right now, and equation A are the 2 equations to be solved. And we're going to be solving for pressure in the oil phase and water saturation. So those 2 equations can be combined and written in matrix form as shown here. So maybe it's good to be able to see this in that context. So T for all of the transmissibility. So it's not just transmissivity, it's a matrix. These ones are scalars. It's a matrix of all of these. Actually, we're here. A matrix of all of these for all of the grid blocks in the domain. That's why it's a matrix. So it is not just one value for a cell. It's for all of the grid blocks in the domain. So it's a transmissibility matrix shown here, multiplied by your solution vector. A solution vector is also known as your vector of primary variables, which is basically shown here. It's a combination of the solution variables in all of the grid blocks. So in grid block 1, we need to find pressure in the oil phase and water saturation. In grid block 2, we need to find pressure in the oil phase and water saturation. And you continue to the last grid block N, you need pressure in the oil phase and water saturation. So this is what your solution vector looks like. The screen just froze. Good. So we move on to D. It's your accumulation matrix. Again, for all of the grid blocks, right? And for grid block 1 is the D11, D12 on the first row, D21, D22, which we had shown before. You see D12 and D11 correspond to the water equation. So we actually put the water equation first. So it's from the water equation we get pressure. It's from the oil equation, which is the second row, we get water saturation. And all of that corresponds to the first grid block, which is why we put subscript 1 here. And we have another matrix like that for grid block 2 all the way to grid block N. And that is your accumulation matrix. It was obtained from the discretization of this, right, for any phase alpha. Good. And as you can see, it's a block diagonal matrix, meaning everywhere else is zeros. So it's zeros in blocks, right? Or blocks of zeros everywhere else. Delta T is just time step size. We already talked about the solution variable. This is at the current time step. This is at the previous time step. This is at the current time step. And the remaining conversations we're going to be having is going to be what time step are you going to use for these values, like transmissibility matrix, accumulation matrix, and the source or sink matrix if there is one. So Q stands for source or sink, meaning your wells. Your source means you are injecting, so that's your injection well. Your sink, your source means you are injecting, that's correct, and your sink means you are producing, and the only difference is the negative sign in front of it. The last thing I'm here to talk about is the transmissibility matrix, T. So the transmissibility matrix is written here, and it's a block tri-diagonal system for 1D flow. So this problem we're solving is for 1D flow, right? At grid block I, you have 1, 2, that's your second block, and actually that's wrong. Let me use a different color. You have 1, you have a different color, 2, that's why I said it's wrong, and then you have 3, and this will correspond to grid block I minus 1. This will be the grid block I, and this will be grid block I plus 1. Whatever is here will be similar to what is here, which is why I didn't bother writing this, but they are all blocks. It's 4 terms. This is also 4 terms, corresponding to the flux contribution from the left-hand side, from the grid block on the left, the flux contribution from the grid block on the right, and this is the flux contribution to the current grid block, I. And it typically has more terms in it. So this is the structure of your transmissibility matrix. All of this is just to give you a pictorial view of how it works. And then for those that love to implement this in code, it's pretty much laid out for you. So for two-phase 1D flow, which is what we just did now, what you have is a blocked tridiagonal system. What if it's 2D? You get a blocked pentadiagonal system. Why? In addition to the grid blocks on the left and right of this cell, which will look just like this, you will have grid blocks above and below, like this and that, which will be, we like to use east, west, north, whatever. So instead of left and right, we'll use west and east, then we'll use north and south. Contribution somewhere here, there will be another contribution to the right of these in the matrix. And we will have indices I plus 1, J plus 1 for the grid block to the right and yeah. Actually, you can have something on the diagonal. Basically, what I'm trying to say is this will be I. This will be I, J plus 1, right? This will be I, J minus 1. This will be I minus 1, J. This will be I plus 1, J. And that's why I said you can't have anything here, right? It's a 5-point stencil showing these 5 points. This doesn't contribute. Good. So that's what you will have for pentadiagonal systems. There will be 5 items corresponding to these 5 on each row. For 3D, two-phase 3D flow, what do you think you will have? A blocked heptadiagonal system. So there will be 7 blocks of non-zeros along the diagonal of each row, basically. Everything else will be zeros. And at this point, I think we now have all we need to be able to talk about the solution schemes using the matrix form of the equation. And I'll do that in the next video.